Hey everybody, MoNaCo here.
And Mills.
Second to last video on our periodic table unit. We're really getting into page 23 and 24 in our pack. We're learning about the shielding effect and the first trend in the properties on the periodic table called atomic radius. And these trends are what you're going to see most of your test questions going to be on, because that's really the important part of the periodic table.
Yeah, this is the nuts and bolts of do you know what the information that's really in there is telling us?
Do you know the hidden information?
Right.
Because anybody can read groups and periods and all that kind of stuff. Memorize your vocabulary, you got the names.
Right.
But you got to know these trends, and unless you take this to heart, you're not gonna.
Sure, and some of them you can actually depict in Table S, which
You
is
can
nice.
if you do a bunch of graphics. But the reason why all these trends exist is something called the nuclear shielding effect. Up on the top here, we've got two different pictures that I picked out that I really, really like a lot myself. Basically, the nucleus of the atom contains all the positive protons. And as we go across a period, you're adding more protons to that nucleus. So the protons in the nucleus are becoming more positive in their magnitude size as you go across the period. Now, we are also increasing the nuclear charge as we go down a group because there's more protons in the nucleus. It's just how it is. So the nuclear charge in the nucleus is called the Z. The Z effective. The effective nuclear charge is changed as you add layers of electrons. Okay? Nuclear shielding effects refers to the ability of the kernel electrons to mask the pull of the nucleus. So the nucleus is pulling on the outside level of electrons. And depending on how many levels of electrons you have in between, the effective nuclear charge, or Z effective, changes. In the phosphorus atom here, for example, there's 15 protons in the nucleus, and it's pulling on the 5 valence electrons on the outside ring. But if you look there, we've got 10 electrons in the way. So the more electrons that are in the way, the less effective the nucleus is at pulling on the valence electrons.
It's kind of like those kernel electrons buffer, if you will.
They block.
They block.
They block the pull for the nucleus on the outside ring. And we know the outside ring has everything to do with the reactivity of the elements. So how hard that outside ring is held determines how reactive an element is.
Right. And so we're going to react one of two ways. We're going to lose an outside electron, or we're going to gain. So we could be talking about losing this valence electron, which the effective nuclear charges that pull in.
It's kind of weak, so it loses the outside ring.
If I get really big.
Right.
And
or if it's really strong, it'll pull electrons from other places and add them into its outside ring.
Right, and we're going to have to break down what the vocab words are for those two things, and we're going to get there. So cause and effect, moving across the period. The number of kernel electrons does not change as I move across the period, but the number of protons does increase. We talked about that. Okay, so this has a resulting increased effect of my nuclear charge because now I have more protons in the middle, but I don't have any increase in my buffering in between those outside electrons. The same number of buffering, so if you look at phosphorus with 15 protons, and I have these 10 inner electrons, well, if I move to the next element after phosphorus is sulfur. I'm going to have 16 protons with sulfur.
And only 10 electrons buffering.
Right.
So the effective nuclear charge will be
increases.
Plus 6.
So now it increases.
And it has a stronger pull for another element's electrons. It's the basis of the beginning of the bonding unit that we'll be doing.
Sure. Everything in bonding will.
And all the trends that we're about to talk about can be related back to this idea that the proton is positively charged and the nucleus has got them all. And the valence electron shell is negatively charged.
And we know that positive and a negative
attract.
There you go.
And whatever's in between causes that attraction or repulsion to be stronger or weaker. End of story. So the number of kernel electrons does increase as we go down a group, resulting in a decrease in effective nuclear charge. More repulsion. Essentially, we're adding an entire another coat or jacket or blanket of electrons between the nucleus and the valence shell every step we take down. So we get a decrease in effective nuclear charge.
So we are increasing protons as we go down, but that increased layer adds that layer of buffering, which kind of negates it.
Right. It slows things down a bit, for sure.
Go. So now on to our first trend. Here in the picture we see the radius of different atoms in the periodic table, right? As I go across the periodic table,
you can see the radius decreases because the effective nuclear charge is increasing. There's more protons, while the shielding effect stays constant. The buffer electrons, the ones in between the valence shell and the nucleus, haven't changed, so their effective nuclear charge is increasing, pulling the outside ring of electrons in closer to the nucleus.
Sure. And this does kind of seem not right.
Right. I'm adding more electrons, mister. Shouldn't I get bigger?
And more protons. I'm adding lots of stuff.
I should get much bigger, but the attraction from the nucleus to the outside electron shell trumps all.
You're right. I got so many more magnets in the middle now, pulling harder and harder.
On the electron shell, which is equidistant from the nucleus. So.
Beautiful. So now as I go down a group, the atomic radius will increase because the number of energy levels is increasing, which is increasing that shielding. I'm basically just adding more layers. Think of that onion.
Yeah.
As the onion grows and gets more and more layers, it's going to get wider.
Bigger. Yeah. Bigger. More electron shells. They have to space out themselves so they can all fit around. More shells, bigger atom. The biggest atoms are over here in the bottom left corner. The smallest are up in the top right.
There you go.
Yeah. So you need to know what shielding is and the atomic radius trends within the periodic table. If you do a search on shielding, you might have some trouble. Let's be honest. So if you're really not getting this idea, come talk to Milks or I. We'll help you understand it a little bit
We'll
better.
draw some pictures on the board.
Yeah, hopefully give you a better idea
How are
if
we
you're
gonna do it?
having trouble with it.
Right.
Note, if you need to learn the atomic radius trend on the fly, it's easy to do because you got to pick some elements in the same group or column and look up the radius on table S, and just kind of do a little chart, a little table.
That information is there, guys, so do not guess.
Yes. Just put them in order, see which size it's doing. Is sizing going up or going down?
You don't got to do every element. Pick one on one side, one on the other. Maybe three, one in the middle.
The trend persists, which is a good point. They don't change crazy random sizes. They go from big to small.
Ooh, we call that linear.
Or small to big.
Right. There you
depending.
go.
There's no exceptions. See y'all later.
Thanks
One
for
more
watching.
video to make.